Hi everyone, this is Dr. Saida Falafini from Cal Poly Pomona. In this video, we are going to talk about one example related to open queuing systems. So consider two operations. On average, 8 customers per hour arrive to stage 1, and on average, 17 customers per hour arrive to stage 2. These are the rate of arrivals from outside the system to any one of these stages. Stage 1 provides service with an exponential rate of 20 customers per hour. Stage 2 provides service with average 30 customers per hour. After completing service at the server 1, half of the customers leave the system, half of them go to server 2. After completing the service at the stage 2, 3/4 of customers leave the system, they're done and leaving the system, and 1/4 of them return to stage 1. And then we want to know what fraction of time is server 1 or server at the stage 1 idle. So we also assume that service inter-arrival times and service times have exponential distribution. We also assume there are infinite space between in front of each one of the stages, infinite space for waiting in front of each one of the stages, and also let's assume in this problem there is one server in each one of the stages. Let's assume that. So we want to calculate this. What fraction of time is server at stage 1 idle? Okay, so tell me first how this system fits the definition of a open queuing system. What is the first thing that tells you this system falls under the category of open queuing system?
That the customers can arrive from outside the system to any stage.
Exactly. 8 customers arrive to stage 1, and then 17 customers per hour arrive to stage 2. So that immediately shows that the customers or entities from outside can arrive to any one of these stages. If it was queuing system in series, they go to stage 1, and then from there, everyone goes to stage 2. But that's not the case here. What is the other important thing here that gives you, again, some hint that this is an open queuing system?
Is it that 3/4 of them leave and then 1/4 of them go back to stage 1?
Yeah, so one of them is here. It says after completing service at stage 1, half of them leave, half of them go to stage 2, half of them leave the system. So again, it's not like queuing system in series, but everyone who finishes the stage 1 has to go to stage 2. Half of the customers that finish stage 1 can leave the system, and only half of them go to stage 2. Similarly, for stage 2, it's not that everyone who finishes stage 2 has to leave the system. Only 3/4 of the customers leave the system after stage 2, but 1/4 of them go back to stage 1 to get some other services and so forth. Okay, so that's again another important characteristic of open queuing systems. And we have the rate of service of each one of the stages, stage 1 and stage 2, and we have the rate of arrival to each one of the stages. So we are good. We can start analyzing the system. And the very first thing that I want is what fraction of time is server at stage 1 idle. So that one's the fraction of time that the server at stage 1 is idle. But before we get to that, let's tell me that what is the type of system at any one of these stages that we are talking about. So this system has 2 stages, stage 1 and stage 2. So in each stage, we have what type of queuing system?
They appear to be MM1.
MM1. So to be able to analyze any one of these queuing systems, I have to find lambda j associated with each one of them. Lambda 1 and lambda 2. And I also have to know mu1 and mu2. For mu1 and mu2, it's easy. So it's given to me here. Stage 1 provides service with on average 20 customers per hour. Stage 2, 30 customers per hour. So mu1 is 20 customers per hour. Mu2 is 30 customers per hour. But for lambda 1 and lambda 2, which is the rate of arrival to these systems, either from outside or from inside the system, I have to calculate that. For lambda 1, the rate of arrival to the first stage is R1 plus, what are the scenarios where entities can come from other stages to this stage. So basically for stage 1, R1s are the ones that are coming from outside, and
R2?
R2 you said?
Yes.
Yeah.
But R2 goes to stage 2. R2 doesn't come to stage 1 completely.
Like an R2 one then?
No, so again, let me. So basically, what happens is that I assume that if I calculate the total rate of arrival to this system, and that's lambda 2, some percentage of them come to this system as well. So that's why in the formula here you see, I don't say R2 here, that, oh, R2, whatever has gone to a stage I, some of them are coming to a stage J. I say lambda I, meaning that for stage I, let's calculate the lambda I, whatever entity has gone to a stage I to get processed, either from outside or inside. And then from those, some of them go to stage J to get processed, and that's lambda I multiplied by Pij. So I have to do the same here. So I don't say R2 multiplied by P21. So I assume that lambda 2, whatever is the rate of arrival to stage 2, some of that is going to come to stage 1 to get processed, right? And I'm going to show that property by P21. Everyone agrees?
That's just the probability of that happening, right?
Yes.
Yeah, if that happens. So everyone can understand why I don't put R2 here and I just put lambda 2? Because remember, lambda 2 is lambda 2 includes R2. Lambda 2 is R2 plus a bunch of other things. So lambda 2 captures the total rate of arrival to stage 2. And I want to know that, and then from that, some percentage come to stage 1 to get processed as well. So I put lambda 2 here. And okay, and also the general scenario. So remember also one more thing. Here in the formula that I wrote, I say for any state J, you can go from any stage I here. But when I put I from 1 to K, I didn't say I is not J. I said I can be any other stage, any stage. What does that mean? That means when in this system, the entities that come from inside to stage 1 are the ones that are coming from stage 2, or the ones that are done at the stage 1 already, but they may need to go back to stage 1 again for some additional work or something like that. So that can happen too if we need to. So then, then the other thing I need to put here to capture all the arrivals to stage 1 is also whatever is rate of arrival to stage 1 multiplied by the chance that when you are done at stage 1, you go back to stage 1 again for some additional work. So that is the formula that tells me what is happening at, what is the total rate of arrival to stage 1. And I'm going to write the same for stage 2. But before we do that, let's calculate this one and see if we need anything else. So here, lambda 1 is, what is R1? On average, 8 customers per hour arrive to stage 1, right? That's what we mentioned here. These are the customers that come from outside to stage 1. And 17 customers per hour goes from outside to stage 2. Okay? So then R1 is 8 customers per hour, and R2 is 17 customers per hour. R1, remember, is the rate of arrival from outside to any one of these stages, and the ones that are given in the problem already. So R1 is 8 here. Lambda 2, obviously, I don't know. That's the total rate of arrival to stage 2, which I haven't calculated yet. I'm actually in the process of calculating lambda J. So lambda 2, I don't know. What is the probability that when an entity is done at the stage 2, it goes to stage 1 for some process?
0.25.
at stage 2 here. After completing the service at stage 2, 3/4 of them leave the system and only 1/4 of them go to stage 1, right? So after you're done at stage 2, the chance that you go to stage 1 for some other processes is 1/4. So P21 is 1/4. And then for lambda 1, again, I don't know it yet. I'm still calculating. What is the probability of P11? The probability that you are done at the stage 1, but you stay at the stage 1 to get some operation again or things like that.
1/2.
Where does it say? It says after completing the service at the stage 1, half of them go to stage 2, half of them leave the system. Is there anyone that stays in stage 1?
No.
No. When you're done at the stage 1, half of them leave the system, half of them go to stage 2. And no one stays at the stage 1. So then P11 in this scenario is 0. But that's not the case always. In this example, P11 is 0, and that's perfectly fine. So then here what I have is lambda 1 equals to 8 plus 0.25 lambda 2. That's one formula I have. Obviously, I cannot solve it because there are 2 unknowns here. So I need one more equation. So let's write the formula for lambda 2. Rate of arrival to stage 2. Okay, so this one. Tell me what are the components of this. So all the entities that go to stage 2 to get the service. Some of them, go ahead.
17 customers for the R2.
Yeah, let's tell me the formula first. So some of them are the ones that are coming from outside. That's R2 plus
lambda 2 times.
Can you do lambda 1 first?
Lambda 1 times P12.
Okay, so what does this represent?
The probability of customers that are at stage 1 that go to stage 2.
Yeah, so those are some of the customers that are done at the stage 1, and now with probability of P12, they go to stage 2 to get some operation. And then who else is at the stage 2 or is coming to stage 2 for some process?
Lambda 2.
The ones that are already at the stage 2, they are done, but they may need to go back to stage 2.
So P22.
P22. And that is 17 plus P12. What is P12? Probability that you're done at the stage 1, but you're going to stage 2 to get the process.
Is that the 50% one?
Yes. Half of them, 50%, go to stage 2. And what is the probability that if you're done at the stage 2, you just go back to stage 2 to get some work done? If you're done at stage 2, yeah, 3/4 of them leave the system, 1/4 of them go to stage 1. So there's nothing that is stays at stage 2 to get the work done. So then this is multiplied by 0. The lambda 2 equals to 17 plus half of lambda 1. That's the second equation. So now I have 2 equations. One of them is this one. That's my first equation that is composed of lambda 1 and lambda 2. This is my second equation that has lambda 1 and lambda 2. I have 2 unknowns, 2 equations. I can solve them. And when I solve these 2 equations, I find that lambda 1 is 14 customer per hour. And lambda 2 is 24 customer per hour. Okay. Now I have lambda 1 and lambda 2. I have mu1 and mu2. I know each one of these stages is an MM1 system. I can easily calculate anything I need. So the first question asks me, what fraction of time is server at stage 1 idle? What do I need to calculate for that?
Mu pi naught.
pi 0. And to be able to calculate that, pi 0 is 1 minus rho, and rho is lambda over mu, lambda 14, mu 20, and that's going to be 0.3. So server at the stage 1 is idle 30% of the time. The second or part B, so I need to calculate expected number of customers in system. What do I need to calculate here?
L.
L. Expected number of customers in the system. So let's calculate L for stage 1. That's lambda 1 over mu 1 minus lambda 1. That's going to be 7 over 3. L2 for stage 2 is going to be lambda 2 over mu2 minus lambda 2. That's going to be 4. So then the average number of customers in the system total is going to be 7 over 3 plus 4. That's going to be 19 over 3 customers. These are the customers at the system at any point of time, average number of customers in the system. And then in part C, if I need to calculate average time customer spends in the system, what do I need to calculate here? W. So to do that, I can just use the Little's formula, L equals L over lambda star. And what is lambda star here? Remember the formula, the total rate of arrivals from outside.
It's R1 plus R2.
Yeah, plus R2. In the system, there are 2 stages, so R1 plus R2. That's going to be 8 plus 17, 25 customers per hour. And then W is going to be 19 over 3 divided by 25. And then that's it. So, and then let's say another part. What happens if server 2 can provide service to only 20 customers per hour? So for server 2, we calculated lambda 2, which is the rate of arrival for stage 2, right? The rate of arrival is 24 customers per hour. So that's the total rate of arrival of entities to this system, the entities that need to get processed. So that's the rate of arrival. And then it says what happens if the rate of service goes to 20. What is a very obvious thing you can learn? You can just say from here.
Well, the row is going to be greater than
Exactly.
1.
It will explode.
Yeah. So if you look at rho, lambda over mu, so that's 24 over 20. That's greater than 1. 24 customers per hour arrive to the system, only 20 of them per hour on average can leave the system. So over time, the number of customers that are left in the system is going to accumulate and the system is going to explode at some point. So this system is not, if the rate of service of a stage 2 is going to be 20 customers per hour, the stage 2 is not a stable queuing system that we can analyze. This system over long run is going to explode for having infinite customers in the system.